So today, staying on. Is it? Hello? Yeah, it is. So you just heard that on your TV. So to talk about hypothesis testing, again, this is stuff, we're working into talking about stuff, new stuff, but I got to get you back to where you were from 21-26. And maybe this is a touch more advanced, but probably not too much. So there's three things we need to say we have a causal relationship, right? Three things. The first is temporal precedence. That just means that causes come before effects. To say X causes Y, X has to have happened first. The beautiful thing is our universe works this way, so that's really nice. Causes can't come after effects. Okay. How do we deal with that? Well, obviously, we just designed an experiment properly. We have to eliminate alternative explanations. That's also pretty easy to do with, well, maybe a little harder to do with experimental design. We do that with random assignment to groups, typically, to make sure groups are similar. We might use matching now and then, but not that often. Might use it though. But we just want to eliminate alternative explanations. Again, that's a design question. That's a design question. Finally, we want to make sure that covariation happens. In other words, as X changes, Y changes. So as the independent variable changes, the dependent variable changes. So if we have that as the dependent variable changes, the independent variable changes, covariation, that there's no other possible explanation, because we've designed the experiment well, that we get a change in Y and we get a change in X, and that X comes before Y, we can then say that X causes Y. This is a cornerstone of the scientific method. This is an important thing. Right? And as I say here, the first two can be easily dealt with, more or less, through experimental design. This is why you take 21-27 and suffer through it and be bored. Because you have to learn how to design experiments properly and to spot poorly designed ones. Okay. But the third thing here, that's where statistics comes in. But we need all of these things. So when we say we have a statistically significant result, that's the covariation thing. If we have a poorly designed experiment, it doesn't matter that we have statistical significance. Statistical significance is different than practical significance. Right? So if it's a poorly designed experiment, I don't care if you got p is less than 0.05. I just don't care because it's just a poor experiment. Questions about that? Makes some sense, yes? Okay. Okay, it doesn't matter what these are. You want to write them down. Look, I don't care, but they're just numbers. We have two groups. I don't even know what they are groups of. I have completely run out of all creativity. The little bit of creativity I have left is you start making podcasts. So we have two groups. This group has a mean of 66.2. This group has a mean of 71.6. These are actually true. I calculated these. The standard deviation is 7.85. Standard deviation 8.56. Of course, sample standard deviation, not population. You should calculate on my calculator because it has a button that says standard deviation. After I put in some data and I push the button, it gives me the standard deviation. It's a beautiful thing. Okay, great. So we have these two. I don't know what these are, whatever. Maybe they're scores in some kind of test, they look like, right? 70s and 60s, so let's pretend that's what they are. Sure. Okay. So feel free to write those down. The individual scores don't matter a great deal here. And when I say not a great deal, they don't matter at all. Worry a little bit right now about the means and standard deviations if you wish. That's right. For our purposes right now, that's the important thing. Before we do anything, and I don't want to do any statistics with this. I know exactly how I'd handle this. Would be a two-sample t-test. You probably know that too. But just looking at those two means and standard deviations, are those two groups different from each other? Statistically different? statistically significantly different. Don't do any calculations even if you had to do it. Just, can you get a feel for that? Look at that and tell me, do they overlap? Are you confident to say they're different, those two groups? Yeah, neither am I. I think you're right. Nice rule of thumb is you take a look at the standard deviation and just, the mean, and just add the standard deviation. 66 and 76 is, let's see, 6, 7, 73, almost 74. Oh, that captures that. 71 minus 8.5. Oh, that captures, yeah, they kind of overlap, don't they? I would not be confident in saying I have a statistically significant difference. I haven't done a t-test on this because contrary to popular belief, I don't do t-tests for fun. But I would look at these two batches of numbers and say, I'm not convinced there's a big difference here. Like, I don't think it matters. Is there a difference? Yes. So when someone says, is there a difference? Well, clearly, they're different numbers. Yes, there's a difference. But would you be comfortable making a bet? It could be a bet for your money, or it could be a bet for something else. I wouldn't be comfortable putting money down. I get this feeling like group 2, if we did this again with another, what do we have here? 10 data points? Yeah. With 10 more subjects, I'm sorry, participants. We have to call them participants now. I like calling them experimental units. It's the technical statistical term, because that really is, people, if you don't like subjects, you're going to hate experimental units. If I get 10 more of them, I'm not entirely sure that this group 1 won't be bigger this time than group 2. And that's something, again, that's back to EDA. I just want you, whenever you get a batch of numbers, just to look at them and see if you can think to yourself, do those feel different? You do, and you play with numbers enough, you start to get a feel for that. And that's good. You all had that same feel, so that's makes me feel good. Did I lose my pointer? I don't want to lose. Okay. Okay. Here's a question. This is sort of the question I asked, but it's a little asked backwards. Here's a curve. This would be one of them normal curves. I think they call them one of the normal curves. It's a normal curve. I keep saying normal curve. It's got a mean of 72. I moved it. Can't do that with PowerPoint. I mean, it's smaller. Try that with PowerPoint. Okay. Could these two sets of scores come from this same distribution by chance alone? I think I've got a standard deviation here of about 4. Maybe 5. I made up this distribution. We would not normally know this in advance. But could these two sets of scores have come from this distribution? Both of them. Look at the numbers, if you did write them down, but even don't worry about that. Remember, it was 65 point something, 71 point something, and then the standard deviations both around between 7 and 8.5. Could both sets of scores have come from this? For those of you that did write down the numbers, what's the lowest number in that batch of numbers? 57. Oh, it's 57. That seems likely enough. What's the highest number?
81.
81. Oh, it's only there. That seems pretty likely. Jeez. Those aren't even extremes in those tails, are they? Those are all in the big meaty part of the curve where we all live. Right? People always ask me, how's it going? I say, I'm right in the big meaty part of the curve where most of us live. No extremes. Now, we wouldn't normally think of this. We wouldn't normally think, this is because this is thinking ass backwards that we would normally do. We normally don't know what a potential parent population distribution is. But I'm just doing this for the sake of a sort of little thought experiment. If this was a possible parent population distribution for both sets of scores, hell yes, they could all come from there. If they all come from the same distribution, are the two groups different? No! No, if they all come from the same parent population distribution, the two groups are the same. In fact, that's the question you are asking when you are doing hypothesis testing. Do these groups of scores all come from one population distribution, parent population distribution, or more than one. It seems really likely to me. I hope to all you guys. You guys all see this, why I am saying that? I think it's a fair thing to say. If we had scores in the 40s, like low 40s or maybe high 90s, yeah, something weird's going on. Those are really unlikely. Those are really unlikely. Okay. We just made a decision. The chance is relatively small, usually less than 5%, because we decided to draw a line somewhere. We say it's unlikely our difference happened by chance alone, and we therefore have a statistically significant difference. When I say chance alone, I just mean random sampling. Okay? Let's pretend, I don't know, what do you think the average height of an Oklahoma University student is?
5'8".
Yeah, that's probably fair. Let's say 5'8". And I still don't know that in centimeters. Is that 170?
A little bit higher.
A little higher? 180?
No, 170.
170 is a little too high?
No, 180.
Okay. So let's say it's 170. What is 170? Hey Siri. What is 5'6" in centimeters?
5.5 feet is 167.64 centimeters.
Okay, thank you, Siri. So I think it's probably about 180, 175, 170. Let's say 180. Who cares? Is it possible, let's say it's 180, and I don't care what the standard deviation, let's say standard deviation is 10, that's a little small, let's pretend it's 10. It's possible that we could randomly select people walking down the hall. Not even a good sample, just randomly select people walking down the hall. And we suddenly have an average height from all those people of 210 centimeters. It's possible that we got all the guys on their way to basketball practice. Right? It can happen. It's exceedingly unlikely, but it could happen. And if I said to you, I have found, let's pretend we know the average height of the Oklahoma University student. Yeah, let's say it's a little bit, it is 180. And I said I got an average height of 210 when I measured these 12 guys. And you said, well, then they're probably not Oklahoma University students. You made a very reasonable decision because they live over in that really small part of the curve. It's a very reasonable decision you made. It's wrong, but it's a reasonable one. Right? Or we could, I don't know what's something that's stereotypically not very tall. In basketball, it's easy to find tall people. We don't have a team of small people that do small things. I don't know, I can't think of anything, right? Gymnasts. We don't have sadly, we don't have a gymnastics team. If we had a gymnastics team, that'd be perfect. A women's gymnastics team. Right? You ever watch the women's gymnastics in the Olympics? They're like 20. Well, I'm 26. I'm working on my master's. And you look and no, you're 4. You're 4'9" and you have a tiny little voice. Yeah, if we had a gymnastics team, that'd be a perfect going the other way. Anyway, it doesn't matter. You see the point I'm making. Okay. We have a statistically significant effect. We think we do. We have 2 different groups if we make that decision. Without significance, we have no covariation of x and y. Is that thing on? It's got to be. Well, it seems to be. It better be. So therefore, we have no causation because we need that in covariation for causation. So what we do is we set up 2 mutually exclusive hypotheses, HO, the null hypothesis, or HO, as it used to be called before that took on another meaning, Oh, people used to call it Ho. I'm serious. They really did. Is it because it's there? I'm really worried about this microphone. I don't know. And H sub 1 or H1 or HA or the alternative hypothesis. Sometimes H1, sometimes HA. You see either one depending on the book you read. Okay? So HA is the alternative hypothesis. That's the one that something did happen, that there is a difference. That the two groups, let's say we're comparing two groups, come from different parent populations. HO is the null hypothesis, that nothing happened. The two groups come from the same population. Now we can make mistakes. We can make mistakes. Here we have reality up here. HO true or HA true. We never know that. If we knew that, we wouldn't have to do the experiment. Okay? So we don't reject. So HO is true. Nothing happened. That's all that means. HO true. HA true. Something happened. They are different. Okay? And then we reject HO or we don't reject HO. Note the lack of except HA. We just reject HO, there's only one left. Right? I hear some people say accept HA. Yeah, I don't like that. And do not reject HO doesn't mean accept HO either. It means I don't have evidence to reject it. It doesn't mean it's correct. It means I don't have any way to say it's not correct. Okay? And I know that's a sort of, seems like a distinction, not a difference, but it actually is a real difference. To me, and many other people. It's kind of like guilty and not guilty. No one's ever found innocent, are they? They're found not guilty. They're either guilty or innocent, but they're found not guilty. They're not found innocent. Okay. So, zooming in, if HO is true and we don't reject HO, we made a correct decision, a very boring correct decision, because we found this is saying that nothing happened and we found nothing. It's exceedingly rare, in fact, that at this point you get an article published. If you have one experiment that says, look what I found, nothing. No one's going to really care. Yeah, if you can put a negative result in with some other positive results, it helps tell a story, there's nothing wrong with that. But negative results on their own don't really, I shouldn't say they don't advance science, because that's not true, but they aren't nearly as important as getting some kind of positive results. Now, what if nothing happened, but we reject HO? What if there aren't psychics, because there aren't, but our experiment, because it's going to happen now and then just by dumb luck, sometimes we'll get the whole basketball team. Just by dumb luck, this time, we were able to find out that, I don't know, someone could read my mind. Don't. It's dark. It's very dark in there. We've made a mistake. A pretty fatal mistake. We've just made an idiot of ourselves. Said something that's conceivably life-threatening. Well, not life-threatening, but career-threatening, which is close enough. But also, usually you're going against some theoretical framework, and usually it's like, you better have a good reason to say this is not true. So in fact, that's called a type 1 error. It does happen. This is why you do a thing called replication. You do experiments more than once. Now, what if HA is true? In fact, there is a difference, and we don't catch it. This is like O.J. Simpson is found not guilty. We all know he killed his wife. But, he did. It's just, come on. But he was found not guilty. Okay. So this is you're letting the guilty man free is what's going on here. There's actually is a difference, and we missed it. This is, you're actually pregnant, but the pregnancy test said, no, you're not. It's fine. It's funny how depending on where you are in your life, that's either horrible or great. I mean, rarely is it like, oh, well, whatever. Like we were trying to have a kid. It was like, yay. Had it been like 3 years earlier, it'd be, okay, I guess that's a thing now. Guess I'll have to finish graduate school faster. That'll be easy with a crying baby around. Whereas over here, oh, this is the one that most of you guys probably like right now. I'm not pregnant. The correct decision here, not pregnant, and it said, I'm not pregnant. Here's a bad one. The next one here, if you're not pregnant, right, the type 1 error, and it says the pregnancy test says you're pregnant, what do? Now, I'm not, don't say because you might, you start saying something. Well, what I did, you go, I don't want people to know that I'm pregnant. So, what do? You then go get another pregnancy test. When you're trying to have a baby, you do that. You have a couple. You go run one, and you say, it worked. Okay, go to the drugstore, get another one. Let's be sure. Let's replicate the experiment. This one here is like a weird one for the pregnancy one, because you'll figure it out at some point. Except if you're one of those people, you ever hear about these people? I had no idea I was pregnant. Then I had a baby, which putting on lots of weight in one very specific place. It seems odd. Have you missed that? I guess, I don't know. Never having been pregnant, I guess I wouldn't know. And no, I'm not one of those guys that ever said, we're pregnant, because I wasn't carrying the baby. Oh, we're pregnant. Oh, are you? Oh, say that to guys. Oh, you are you? Are you carrying the fetus together? No, she's pregnant. Be very supportive, but don't take the glory from her. Are you going to be having the pain? No. There's being supportive and then just being a man taking everything over. Right? Because men do that. I don't know if you've noticed that. Let me explain to you girls how this works. See what I did there? Okay. It's a little joke there. A little joke explaining. So, this is a good one. You're pregnant and it says you're pregnant. Or, so one of the other. Or, even better. Levels of processing does affect priming. And I found that with my experiment. That's more of a sciencey one. So again, correct decision here, but uninteresting, but that's okay. It's not a bad thing to get this, and a lot of people in their honors thesis. Almost everyone's honors thesis experiment doesn't work, just to let you know. Easily 2/3 of them don't work. That's okay. It's not okay when you're in graduate school. It's okay as undergraduate. It's with the process, okay? You're not trying to you're not trying to blow the lid off anything in 4th year. If you do, way to go. All right. So we do have then some control. We set the probability of the type 1 error. We say we want a chance of this happening being small, and we usually make it 5%, 0.05. So remember that distribution I had, that could it all come from here? We do something to that effect. We just convert it all into Z scores or T scores or F scores. And then we say, okay, we know then, because that's a standardized distribution of some sort, that we just set. I really don't think this is recorded. Like, I'm not getting there's a little sound level there. I don't know. If it's working, you're hearing all kinds of me going on the thing on the YouTube video, so that's too bad. So we set that value of a type 1 error. It's called alpha. And by the way, in about 3 weeks, alpha is going to mean another thing as well. And that's going to be really annoying, and it's not my fault. Don't blame me. Probably the type 2 error depends on n, the number of subjects, because the more you have, the more accurate your estimate's going to be. It depends on alpha, sigma, that's the variance, or standard deviation, variance, since it was squared, and alpha. And it's called beta. And unfortunately, beta is going to mean something else as well in about 3 weeks. And again, it's not my fault looking at it. It's easily discernible, the two of them, but they use the same Greek letters, which is really annoying. One minus beta is a correct rejection or statistical power, the power your test has. And ideally, obviously, you're going to want high power and low alpha. That's perfect. You don't want to make errors, and you want to detect things that are really there. Questions so far? You okay? You good? Sure. Why does that say that? ZC. Why does it say ZC? Obviously, that was a weird edit that I made mistakenly. What do we set alpha at? No. Yes. Alpha. What do we set alpha at? That's what that should. Why? How did that happen? Very weird. Or ZC, as I like to call it. What do we set alpha at? We set alpha at 0.05. And note the ... It's completely stupid and arbitrary. This is totally because of R.A. Fisher. Now, R.A. Fisher is a pretty smart guy, so we shouldn't say anything bad about him, but like he invented analysis of variance. That was cool. He came up with the first, if you guys think it's biology, the first kin selection model, R.A. Fisher. 30 years before like Hamilton. That's impressive. Yeah, more than 30. But his students were working on the F distribution. Remember the F distribution for analysis of variance? And he talked to, I think, might have been Tukey. Some American statistician asked, what percentage point of the distribution are your students working on? Because somebody had to do all the calculus. Well, I know that to get those series and those curves. And he cabled back, that's right, a cable, Western Union, right, telegram. I don't know, maybe it was a letter. I just like to pretend it's a telegram. He said they're working at 0.05. Okay, we'll do that one too. That's totally where it comes from. Somebody just arbitrarily thought, 5% is good. I think we might want to be a little more flexible. I was once told in an article that I submitted for publication, it did eventually get published. When I discussed a result, that had, it went along with everything else theoretically I'd written, it went along with all the other data, it just was at, I kind of rounded it, it would be 0.05, but I thought I'm going to be intellectually honest, and I'm going to say 0.0504, and I was told by the editor not to discuss non-significant effects. I could have just rounded that to 0.05 and that would have been fine. But no, I was trying to be nice. Seems a little silly, doesn't it? It wasn't like I was saying, so therefore there's life on Mars and it controls our minds. It wasn't anything like really crazy that I was saying. And it caused AIDS and it could cure cancer. Wait, what? That one did quite a breakthrough. I think you want less than 0.05 on that one. I said it was something about a comparative thing, and I was doing a comparison between two bird species, and it worked perfectly with all kinds, like the other 20 analyses in the paper. I've not discussed non-significant effects. Oh, do shut up. That was the same editor, by the way, that told me to call my subjects. I can't use subjects because we use participants now, and I said I'm not calling pigeons participants. They didn't say I could say for. I'm sorry, I'll call them animals maybe, but I'm not calling them participants. There's no way I'm writing the word participant for that. Pigeons don't feel exploited and like they don't feel bad because I call them subjects. They're pigeons. That's the argument I won. I didn't win this one, which is too bad. I mean, when you think about this, when would you want to change? When would you want to change to be a little more liberal? Like you say, okay, there's no problem with maybe a 10% chance or a 15% chance of type 1 error. Do you think of that possibility? Please.
I can't pick one specific, but the outcome would be like if you're wrong, it doesn't make too much of an impact.
Yeah. But if you're right, it's a big impact. Yeah. You got what?
Pulling on chocolate from a bed.
Yeah, but that's non-important. Yeah, fair enough. Let's think of a real world thing, because that doesn't really happen. What about if they tell you to boil your water? You got a boiler for the city. Yeah, I'd like it to be at, you know what, I'm fine with it being 0.15, about a standard deviation. So 15% of the time they're wrong, and I have to have the horrible inconvenience of boiling my drinking water for 5 minutes. I'd rather that than, oh, I don't know, dying. Right? Most of us here probably, most of you guys have never lived in a community where you can boil your water. Is that true? Have you ever been where there's a boiler? Because I have. Because I lived in Newfoundland. And every spring, because of the runoff from the mountains, our drinking water, you just get it would show up. It'd be like a thing, you hear it in the news, and you have to boil your water. And most of the time, you didn't find out when you first moved there because you're mainlander. You don't find those kind of things out, but you listen for that. So for 3 days, we're brushing our teeth and all that stuff and drinking coffee. And then you find out you should be boiling your water. Because of what's called beaver fever. Giardia. It's very unpleasant. There's a lot of pooping. So, but we were fine because, of course, they were just being they weren't being very conservative. They should be. I mean, you don't want it because a little kid or an old person can literally die from that. So instead, oh no, I have to boil my water until you are smart and you install this really cool filtration system in your house. And you don't care. And you laugh at your friends boiling your water. Secondhand smoke would be another. You know, secondhand smoke, most of the data are very not clear that as they make it out to be that it causes all kinds of horrible things. Right? So the idea, for example, that smoking is banned indoors everywhere. It's worse than being Hitler is smoking. But you know what? I'm okay with that. You know why I'm okay with that? Because first-hand smoke's really bad for you. But it makes you look cool. But really, seriously, think about it. So the inconvenience is you can't smoke. I can't, if I still smoked, I couldn't smoke in my office. That's not that big an inconvenience compared to I could also be giving students lung cancer. Yeah, okay, you know what? If it's not 0.05, I'm still okay with it. I'm still okay with it. On the other hand, what's one where you think you'd want to go the other way? To say 0.01 or 0.001. Do you need more conservative? Think of an idea or a situation? Where would you want to be really conservative in science? Science is already really conservative. Where would you want to be really conservative?
Medicine?
Some medicine. What kind?
Like surgeries or something, maybe?
If we already have a treatment that works, and this thing we're bringing in has bad side effects, yeah, I would agree there. Yeah.
Disclosing that there might be nuts or other nuts exposed to the food we eat.
Yeah, that's not bad at all, actually. The idea of peanuts. The potential of being peanuts. That's actually pretty good. No, we want to go the other way. What am I saying? We want to go the other way with that, though. We want to be just like we do with the boil oil with peanuts. Because getting a little bit of peanuts will kill you if you have a peanut allergy. Let's think of one. I don't know. How about anything that blows the lid off anything? Oh, it turns out things can mold faster than the speed of light. You better be damn sure of that. Do your analysis again. Do the experiment again. Turns out there's life on Mars. Better be sure. Stuff that blows the lid off something, you ought to be really conservative about. Something that where we already have an effective treatment, very good answer there. But we have a new potential treatment, but it has nasty side effects, let's say. Let's be damn sure it works better than the other thing first. Right? And that's often done now with treatments with clinical trials for drugs for managing AIDS and things like that. They actually usually move the alpha level. Because the treatments now work okay. Like if it's antigen, it's not acute. So I think we want to be a little more liberal, sometimes a little more conservative. what some journals are now going to is what's called exact p-values. So instead of just saying you reject the null or you don't reject the null and you use 0.05, they're saying present the p-value and then that you got, and then interpret your results based on how strongly that p-value correlates, like how small that p-value is that you end up with. Is it way less than 0.05 when you look up the p-value in a t-table or whatever? So some things are going to that. And I think you're going to see more of that as time goes by. Questions? Any questions? We got done early today, but that's okay. You had a quiz, right? You don't want to start a new topic, do you? You feel cheated out of your tuition? Anyone? No? No, I don't think so.
No, it's okay.
All right?